a gas, you just go to the gas station, and in 2 minutes you have refilling of the gas. But if you have to change, for instance, the gas tank, it will take much longer. So the customer may not like that. So the other idea was just to use the same gasoline they use now, but then in this case your car must accommodate the system. It must have the hydrogen producing, cracking, then the purificator, and then the fuel cell. This also occupies a very big, huge volume. So some people thought to use methanol instead of hydrogen. We will see how this works. And this was very, very much appealing because methanol is a bit dangerous. You cannot drink methanol. At least you can drink it, but it's not good for your health. And also, as we will see, we will can have also a cell using with ethanol. You can drink ethanol. Okay? So you can have a car working on ethanol, wine car, whatever, whiskey car. And it's a liquid. So the idea now is to have a car which can use liquid refilling, and most of these problems are solved. And a lot of money was then invested in this idea. But again, we have some problems here. What time do we have? Okay, another 15 minutes. Let's first see how this works. Now, the difference between a polymer membrane fuel cell, the one that we have so far discussed, and a direct methanol fuel cell is that in the first case, the fuel is hydrogen, while in the second case, alcohol, for instance, methanol. The other part is exactly the same, oxygen. The electrolyte is exactly the same membrane. The catalyst changed a little bit. Instead of being platinum, we must have a kind of alloy, platinum-ruthenium. But then the electrostructure is exactly the same, because in the case of a polymer membrane fuel cell, this was a very small particle of platinum deposited on a carbon substrate. In this case, instead of having the platinum, we have a small particle of platinum-ruthenium. Exactly the same thing. It's also very easy to do, because it's just replacing just taking a normal polymer electrolyte fuel cell and just operating it, instead of using hydrogen, using methanol. And here you have some indication how this thing works. Okay, you see that here, at the negative electrode, instead of having refilling of hydrogen, we have our methyl alcohol with some water. Okay. Here you have the gas diffusion layer, and in this case it's a liquid, but the liquid can go through. And here you have the MEA, okay, and in which we have electron exchange to drive all the electrochemical reaction. And you have, don't look at this at the moment, you have protons going through to the membrane and arriving to oxygen. And maybe here you see it better. So here you have the mixture, methyl alcohol and water arriving here. This is the gas, the MEA. And you see the reaction taking place here is written down below. Below is this methanol plus water giving protons plus CO2. Okay, so here you have formation of protons which go through the membrane exactly as before. And you have CO2 which comes out from here, right? Here instead you have oxygen arriving here and methanol, proton, and then you have the user reaction of oxygen reduction. But you see from here a first problem. The first problem that we are producing CO2. So this system is not as ecological as a polymer electrolyte fuel cell, because a polymer electrolyte fuel cell is giving you only water. Here instead it's producing CO2. The second problem, and we discuss that in detail pretty soon, is that in this membrane you have not only the passage of proton, but also some water can pass through, which is already a problem, but the most problem is this one. Methanol is going through the membrane. Let's first see why we are using platinum or ruthenium here, COH. And ruthenium to absorb OH. Because only with these two combinations, you see, platinum COH plus ruthenium OH, you obtain at the end the final product, which is CO2. Okay? So for this particular cell, you need not only platinum but also ruthenium. So this is called bifunctional mechanism. Bifunctional means that we need two materials to drive reaction, so platinum and ruthenium. A bit different from before, but then the MEA is formed exactly in the same way. As I said before, in a pure membrane fuel cell, you have only platinum dispersed on a carbon substrate. In this case, you disperse on a platinum substrate a platinum ruthenium. Then all the other is exactly similar as before. But you must be a little bit careful here, because when you prepare your catalyst, you can do it at under different condition, temperature condition, and you see here that here is reported typical curve which gives you the current density versus the potential, and the loading is all the same for all these three cases. And you see that for the case when you prepare your catalyst at 600 degrees, because this is prepared with a solid state reaction, you have the voltage at which we have oxygen evolution. I think this is due to oxygen, is this value, okay? And of course, it is very important that the voltage is the lowest as possible, because as low as the voltage, as low is the overvoltage. I mean, as low, well, let's put it this way. As lowest is the voltage, is better. The better, because you don't have to apply to lose voltage in the operation. And you see that when you operate at 60 degrees, the maximum current that you get is this one. It's not very much. Don't be mistaken by this. This means that that curves are obtained at 25 degrees by using different catalysts made at the beginning, synthesized at different temperature. In other words, this is a 25 degrees operation by a catalyst which is prepared by firing it at 60, 600 degrees, 500 degrees, 430, 470. And these curves tell you that gives you the voltage and the current. And you see that the lower is the voltage is the better, and the higher is the current is the better. So at 600 degrees, you will have a very high voltage and a very low current. At 500 is a bit better. You have a little bit lower voltage and a higher current. For the sample made of 130, even better, because the current increases. And the best behavior is given by the, the sample synthesized at 417 degrees C. And here, in fact, is reported the activity of the various catalysts. And you see that the best condition is given by the catalyst prepared at 470. And why this happens? This was one of the main problems to understand why this happened. And this is related to the crystallinity of the sample. And this is quite understandable because you have the same operation here. So the red dots are the particle, the catalyst particle, and this particle has to absorb the species to make the reaction go. And now it's well known that this is related to the situation, crystal situation. You see that we start from the sample prepared at 600 degrees, the green one, is very, very high crystallinity. This is an X-ray pattern. I don't think I have to explain you what an X-ray pattern is. I'm sure that you have all a very clear idea. So in X-ray pattern, when you see all these peaks, that means that you have very crystalline material. When instead you go to the black curve, you lose all these peaks, so you are in an amorphous situation. So neither the very high crystallinity is functioning very well, nor the very low crystallinity. So we need something in between, which is exactly the situation of 470. Okay, I think that we may stop here.